Hello and welcome. Today we're going to be doing some examples of Laurent series calculations. And so let's briefly write down what the Laurent series is. So if I have a function f of z that is analytic in some domain uh, domain D, and that domain may be nearby a point of non-analyticity. So you have some point z naught where you're having trouble, and then of course the domain D is there. And so the idea is that we can write our Laurent series is as follows: f of z is equal to the sum of n equals 0 all the way to infinity of a n z minus z naught all the way to n. All right. Likewise, I can write. There's another branch to this series. So this is the Taylor-like part. And then we have Bn, n going from 1 to infinity of z minus z naught. And these are negative powers of z minus z naught. So in fact, I can actually rewrite this in a different form. I can rewrite this as follows. And is all the way from negative infinity to infinity of what I'll call Cn, z minus z naught, all the way to, for n. Now n ranges from negative and positive powers, and so this is just a little bit more compact way of writing it, and Cn, of course, just equals an for n's greater than or equal to 0, and it equals bn's for n's less than or equal to negative 1. All right, again, what are the an's? Well, the an's, or the bn's, now I'm going to write it this way. The cn then can be written in the following form. And now I have a one formula for all of the coefficients in this more compact form, which is the integral over some c, which we can now is some positively oriented contour inside our domain of analyticity, which I'll call C there. And it is f of z all over z minus z naught dz. Okay, so there's our nice formula for all of our coefficients. So now what I'd like to do is just go through some examples of how to do these calculations. Because many of these integrals, of course, this is a Cauchy integral formula type. Oh, sorry, I'm making a mistake here. There's an n plus 1 up there, right? And now n can range from both negative and positive values. So any integer can be in there. So, so this is a Cauchy integral type formula. So we should be able to actually compute a lot of these. So I'll show you some tricks of how to do this. Okay, so first let's talk about some a really basic example first. So okay, let's say I have f of z is equal to 1 over z. Okay, so first of all, I can rewrite this as 1 of z minus 0. Okay, so I can think of z naught as now being 0. So we have a singularity like that. There's our 0. 0 point now. And so the domain of analyticity could be just anything, any annulus where I take out the 0 point, right? So that can be my domain of analyticity. And in fact, I can make it's analytic everywhere else, so I can make that annulus as big as I like. So the idea then is to use the formula. So again, we have our. So first of all, what we see there is that we're going to. So this is equal to Cn z to the n, where n ranges from negative infinity to infinity, and I could read it right off. Read it off that c negative 1 equals 1 and cn equals 0 else. So it's sort of a trivial. F of z is its own Laurent series if I expand about the z naught equals 0 point. All right, so again, what I'm trying to say here is that's easy. Okay, f of z is its own Laurent series. Okay. So the question that, or sorry, f of z equals 1 over z is its own Laurent series. That is simply one of the terms in Laurent series. All right, but now let's go through and actually just compute, just to make sure we're on the right track here. I'm going to actually write down what the CNs are. I want to actually prove that that's true. All right, I'm going to use the formula. So that's 1 over 2 pi I, integral around some contour that doesn't have 0 in it. And then, so what I'm going to do then is write out the formula, 1 over z over z to the n plus 1 dz. Okay, so clearly let's try doing, so let's try the case of n equals -1. So that becomes 1 over 2 pi I. And so I put a -1 in there, and that becomes a 0th power in the denominator. That becomes a 1 over z then, because this essentially the denominator goes away. We're left with just what was in the numerator up there, dz. And of course, we know that this has there's a very standard formula where this integral itself is equal to 2 pi I. So again, it's 2 pi I all over 2 pi I, which is equal to 1, which is precisely what we had read off immediately from that. So now let's try another one. Okay, let's try c of 0. Okay, so we tried n equals 1. Now let's try n equals 0. And that'll be 1 over 2 pi I, integral around the contour. We put a 0 in there, I have a 1 over z. And then we put a 0 in for n, and that becomes just a power of z there, dz. And that becomes 1 over 2 pi I, integral around our contour of 1 over z squared dz. This has an antiderivative. In d. All right, so we know from Cauchy-Goursat that this has to be 0. So it's 0. All right, and so in fact we can do the same thing here. This would become, for C1, it would be 1 over 2 pi I, integral over the contour of z, 1 over z to the 3rd power dz, which of course is also 0. It also has an antiderivative and so on. But now let's go to the negative end. So we tried at -1. So now do you want to try c -2? Let's do that one. Okay, 1 over 2 pi I, integral over c. Now we put that 1 over z in the numerator again. And now I have a -2 there, so that makes a n. So -2 plus 1 becomes a 1 over z. That becomes in the denominator, that becomes a 1 over z, right? Okay, so then that's dz. So what does that become? That becomes 1 over 2 pi I. And that becomes integral of c of 1. Okay, dz. Does this have an antiderivative? Yeah, by Cauchy-Goursat then, that's also 0. Okay, we could keep doing this. And in fact, maybe it's worthwhile to do c -3, which is then going to be 1 over 2 pi I, integral of c. I think this will be instructive to do this one. But you're going to find out then, of course, you're going to get a second power down there. And that becomes a z to the 1st power in the numerator. Okay, dz. That has an antiderivative in the domain. It's equal to 0. And so on and so forth. Forever. We could do that for all the other values. The only one that picked up a value was the n, a non-zero value was the n equals -1 case, which gave us just a 1st power in the denominator of z. All right, so that, again, you're going to see this over and over again, that this is the one thing that gives you a result that you're looking for, and everything else is, it works just the way you think it was supposed to work. Okay, so let's now go try another example. So we've kind of done that several different ways. So now let's try another one. Okay, so let's try now f of z is equal to 1 over 1 minus z. Okay, so this is something that looks familiar. We know this one. This looks like a geometric series. All right, so for instance, so now let's look at this, right? So if I have my plane here, there's a singularity at z equals 1, right? But we know if I actually expand about the z equals 0 point, if I make z naught equals 0, right? There's a domain of analyticity that's the disk with the modulus of z less than 1, in which case I never actually get to my singularity, in which case f of z has a Laurent series, which is simply actually just a Taylor series, which is just z to the n equals 0 all the way to infinity. Right, so what we're saying here is that if I write that, then that means the c n's are going to be equal to 1 for n greater than or equal to 0, and they're 0 for all the n's less than 0. Okay? All right, so there's a Laurent series, and that's only valid in this disk region there. But what about what if I put z0 is equal to 1? Right? That'll be my another way I can expand the Laurent series a different way, and that goes back to what we've seen before. F of z is equal to 1 over z, which is basically saying that what we have here then is this is actually, if we write it a little different way, it's going to be negative 1 of z minus 1. That's how we would usually write it. In which case what we have is a Laurent series of the form z minus 1 to the nth power, and going from negative infinity to infinity. What we see in this case then is it would imply then that Cn is equal to, just like we've seen before, we have c, it's equal to negative 1, scribble that out there, for n equal negative 1, and 0 else. Again, another trivial Laurent series. Okay, so we could do other examples involving other points to see what we could find, but I'm just going to leave it at that. So now let's try something more applied. Okay, we've done a few kind of charming examples where we already have nice results. So again, here, what this is just a pure Taylor series. And then here is a Laurent series with only one term. So now let's try something a little bit more interesting, a little bit more complex. So let's go back to what we've studied before. Where do these, what are a really important complex function we always talk about in signal processing? We talk about the transfer function t of s. I'm actually back that up. We'll usually put it as a t of z now. We think of that as a complex variable, and that comes from the Laplace transform, and it's some sort of 1 over polynomial in z. Okay, so let's talk about a particular example. Let's say we have a transfer function of the form 1 over z minus 2, z minus 1. Okay, so again, if I were to write what am I looking at here, we have a 1 right there where we have a non-analytic point. We also have a 2 where there's a non-analytic point. So what I want to do now, so I want to expand our Laurent series at z naught is equal to 2. Okay, so again, the domain then, that would imply then the domain is this going to be this region around here. Okay, and so that's all this stuff right here. I can't go beyond that one point there at 1 because then I'd have some problems. So what I'm going to do is I'm going to take a contour that's inside that domain. That'll be my C. Right, and that's what I'm going to use to compute this series. So there are other ways to do this, and the book has a whole different way of exploring this. But I want to give a very direct way where we actually use our contour integrals to find our CNs. Okay, so let's do this. So now, again, we want to find t of z of the form sum n from negative infinity to infinity Cn z minus 2 to the n power. All right, and so we want to find these Cn's. So Cn in this case is going to be of the form 1 over 2 pi I integral around our contour, which is inside of our domain, which we'll call D. That's my domain. And then we're going to have t of z all over z minus 2 n plus 1 dz. Okay, so let's again pick a few important values. Let's try a different values of n and see what we get from this. All right, so the first value I'd like to try is actually let's try n equals minus 1 again. So let's try that. So let's try n equals minus 1. In which case the denominator becomes just 1, and we're left with c minus 1 is equal to 1 over 2 pi I integral of c of just t of z dz. Okay, what is that exactly? Well, we can write that down as 1 over 2 pi I c. And what we can actually see is we can break this up or sort of refactor it in a different way. We can actually put that as 1 over z minus 1 all over z minus 2. Okay, dz. And of course we know from Cauchy integral formula that this top part right there, of course, is analytic on d, right? The singularity point is 1, and we're behind that. We're in this range here, so we're okay. We're far away from 1, in which case we can just evaluate it to be the value at the point itself. So that is actually just going to be 1 over z minus 1, all evaluated at z equals 2, which of course is just 1. Okay, there we go. So that was a very nice result. So now again, I want to we'll get to this in a bit, but that's the value at that coefficient. So let's try a few more coefficients and see what we can find. So I'm going to try now c0, in which case I have a 1 over 2 pi I integral around our contour. And now what we have is the c0. If I put a 0 there, then we're going to have a 1 over z minus 1 all over z minus 2. And now we're going to have a squared, okay? And that's because we have a power here, and we also have a single power in the denominator, and that creates 2 powers in the denominator when you just do everything. And of course, we're going to use the Cauchy integral formula again, but now we're going to be taking the derivative of the function. So what we do is then that becomes 1 over z minus 1. We're going to take its derivative, and we have to divide by 2 factorial. Okay, and of course this is exactly the coefficient. So this is like a Taylor coefficient essentially. And then we're going to evaluate that at z equals 2. So we can do that. That'll be now. Let's do that. So that will turn into minus 1 over z minus 1 all quantities squared, all over 2 factorial, and we evaluate that at 2, we get it's equal to minus 1/2. Okay, good. All right, so now we have 2 of those coefficients. Should we do another one? Let's do c1, and from that we'll get 1 over 2 pi I integral along our contour, 1 over z minus 1, and then we have a z minus 2 quantity, all quantity to the 3rd power dz. Okay. And for this, of course, this function up in the numerator is analytic on our domain, and so we now will take 2 derivatives of it and divide by a 3 factorial. So that becomes 2 times 1 over z minus 1 to the 3rd power, all evaluated at z equals 2, and that becomes then 1 over 3. Okay, and we could keep doing this forward for C2. Yeah, why don't we just do it? 1 over 2 pi I. And then, of course, we're going to, in fact, we can just keep doing this. Then that's going to be 4 factorial. And then we're going to have is a 3 factorial in the numerator, and then a minus 1. So we're going to get a minus 1 over 4 coming out of it. Okay. So we see kind of a pattern here generating as we go forward. In fact, we can see that going on. So let's just go to the next page and now sort of summarize our results here. So again, we have here this f of z is equal to n equals negative infinity to infinity cn z minus 2 to the n power. And what we're seeing there, if I can write this out as follows, it was a 1 and then a minus 1/2. Oh, sorry. So we had that c to the negative 1 term, which actually was a 1 value, and then of course we have to put the z minus 2 in the denominator, because that was the negative 1 power. And then we had a minus, for c0 we had a minus 1/2, and that's the 0, so this is a c0. And then we had a c1, which was a plus a 1/3 z minus 2 to the first power. And then we had a minus 1/4 z to the minus 2 to the second power. And it keeps going up like that. And it looks a little like a logarithmic series that we've seen in the previous video on Taylor series. All right, so then, okay, the question then is, as we go this way, what goes on here for all the negative powers? What happens for c to the negative 2, c negative 2, c negative 3, and so on going that way, all right? Because that's what this series is. It's a series that goes both directions in terms of powers of n. So we have to find those. So now let's try c negative 2. We can put that in. That's 1 over 2 pi I. Integral over our contour of 1 over z minus 1. Z minus 2. That's our transfer function up there. And then what we have to do is put z minus 2. And it's to the n plus 1 power, so that becomes a negative 1 there in the denominator, dz. All right, so of course we can rewrite this as 1 over 2 pi I. And so a negative power in the denominator becomes something that's in the numerator, so we have a integral over c. And what happens then, of course, is that it becomes a 1 over z minus 1 to the z minus 2 power, or sorry, times the z minus 2. And then, of course, this goes in the numerator, so we get z minus 2 in the numerator again. They cancel, dz, and that becomes then integral over 1 over 2 pi I, integral c of 1 over z minus 1 dz. Recall again, though, that our contour is enclosing z equals 2, but the contour is not at z equals 1, right? Our domain is inside of this region here, right? And so the domain that we're integrating over then, this function is totally analytic there. So in which case, we know it has to be 0, right, by Cauchy-Goursat. It's analytic. Okay, so now we know that there's a 0 there. Okay, but what else? Can we go to c negative 3, see if we can get a similar result? Well, it turns out, if you do this, of course, that'll just become a negative 2 there, in which case, what we're going to get out of it is a z minus 2 in the numerator to the first power times z all over z minus 1 in the numerator, dz. And this is, of course, also analytic, in which case it's 0 by Cauchy-Goursat. All right, and now it turns out for c to the n for all negatives less than negative 1, it's going to be 1 over 2 pi I integral c of z to the z minus 2 to this. So we had a 1 power there for the negative 3. So of course you're going to have a negative n minus 2, right? That makes sense then. All over z minus 1. And this is, of course, analytic on the domain that we're interested in, and that, of course, will always be 0. So what we see here is all the negative powers below the n negative 1 are all 0. So the Laurent series is truncated in one direction, but it's infinite in the other direction. All right, and notice that, of course, again, let's write it all out. I should have called this t of z, right? That's what we have here. So I'm going to rewrite that again, just to see if we can kind of make this clear. So t of z is equal to, now I can write this as so that's equal to 1 over z minus 1 and a z minus 2. Okay, looks good. All right, and now what we're going to write this as is 1 over z minus 2. That was the c negative 1 power. And then we had a minus 1/2. Then we had a plus 1/3 z minus 2. Then a minus 1/4 z minus 2 to the second power. And of course, we can keep going up. It'll be a fifth z minus 2 to the third power, and so on and so forth. But notice, of course, the singularity. The singularity that is inside, or I should say the singularity that that is inside of our domain, right? Because remember, we're over here at 2. We had to cut 2 out and make our domain like this. Oops, I should have wrote that a little different. So there's a 1 right there. So our domain is this sort of annular region right there. The one that we're enclosing here, the one that's inside that we had to cut out of our domain, that singularity was to the first power. So we saw that our Laurent series actually, coincidentally if you will, it turns out there's no coincidence here, but it turns out that's also to the first power. And there's nothing below it. No powers lower. So that will turn out to be a pattern you can see a lot. And this series actually was completely, this is of course a Taylor series for 1 over z minus 1 that we computed through the Cauchy integral formula. So now we see we've broken up this transfer function into these two really neat parts. One contains this singularity, and the other stuff here then essentially describes this other part right here. Okay, and so that's really neat. The fact that this Taylor series really breaks out information in a different way. So now we see why, when we're studying transfer functions, these Taylor series or these Laurent series can be very, very important, because they will yield ways of deconstructing or decomposing our transfer function into pieces that can be more manageable. Anyway, this should give you a hint at what's coming up and why these Laurent series are so incredibly useful. So thank you very much.